Yeah, so I realized I might be promising a bit much with the title, but we were asked for titles at some point. I wanted a short, catchy one, and Rosemary said she would appreciate something that had to do with beauty in science and what we do. And I'll mention a couple of phenomena that happen that have something to do with infinities. So Beauty at Infinity was the title. I also wanted to thank you for being an inspiration, both personally and as a scientist. I've always found astronomy and astrophysics to be very inspiring. Certainly as a child, that was my main inspiration for getting into science, and for a while I thought I was going to be an astronomer, and I ended up as a theoretical physicist, so the opposite of you. I think when anyone looks at an image like the one I had on the first slide, the images of the universe, stars, that was a star cluster. They just draw you in, they're compelling, and they're fundamental about the universe, and you just want to understand what's going on, and they're so beautiful. So of course astronomy and astrophysics really have the goods on particle physics there. There's just an obvious visual appeal to the phenomena that you're looking at. They're also part of the beauty is that it's not just something that somebody drew on a piece of paper. It's the universe. It's fundamental. It's really connected with the basic nature of reality. And I think also many of us here as scientists, there's another beauty in what we do, this sort of abstract beauty in the mathematics, the mathematical models, the pictures that we build in our minds of what we study that are hard to communicate. And when we give talks to each other, we're trying to communicate these elaborate pictures and models, mathematics that we've built in our minds of the things that we study. And certainly there's lots of that in astronomy and astrophysics as well. Now I would say particle physics, which is where I work, certainly also has the appeal of being fundamental. It's the fundamental nature of reality, the fundamental laws that govern the universe. That's part of what attracted me to it. It's also got this abstract beauty, which can be hard to communicate, but certainly that's part of why I love it. Not so much, perhaps, on the obvious visual appeal. I was noticing at Open Day that we recently had that a lot of our visual material is the material from astrophysics and astronomy because it's so nice. And in particle physics, it's very hard to visualize things in nice ways. Of course, we can put pictures together of nice kit and light them up in nice ways and try to show people that, ooh, this is cool. And sure, yeah, it's cool, but it still doesn't compete with, images of star clusters and so forth. And there are other things we can do. When we have particle reactions, we can make, pictures of tracks and various kinds of event displays. But even when they're really jazzed up, I think they don't look compelling. And this one, yes, this one is. These are lovely, especially when they're colored and stuff like that. But of course, this is quite far from how we actually look at this data in a scientific way. And I always both was a bit sorry that we didn't have the same kind of visually nice material as astronomers and astrophysicists did. And that a lot of the things that we show people are very technical and also don't really communicate how we look at the data. And I always wanted to try and see if I could come up with something else. What about the abstract beauty, the mathematical beauty of, the theoretical beauty of what we study in particle physics? And many of you know that I spent, a week of my life doing this in LaTeX to illustrate what, proton collision at the LHC, all the elements that go into it. And as a diagram that communicates something scientific, it kind of works. It even won a competition on Twitter for Physics Plot of the Year 2022. And it carries a lot of scientific information, and so it starts to look visually compelling, at least I would say so. But again, in a technical kind of way that we can't really expect undergraduates and members of the general public to be excited about. But at least all of these components, all of this stuff here, the Bremsstrahlung, the hard interactions, all of this stuff represents parts of the underlying mathematical structure. And maybe there are ways that this could be turned into something that would be visually appealing.
It is visually appealing.
Thank you. That's great. I'm very happy to hear that, especially from you. So what does it illustrate? It illustrates structures in quantum field theory. And what do we do when we do calculations in quantum field theory? We calculate cross-sections, reaction rates, event rates. Now, a cross-section really is just sort of an effective area with quantum mechanics and stuff going on underneath, but that's basically what we're calculating, an effective area. And in perturbation theory, we calculate this cross-section with higher and higher detail when we go to higher and higher perturbative orders in this power series in the coupling. And so here's an example of calculating an area with higher and higher detail that mimics some of the aspects of perturbation theory. We get a pretty good guess at leading order, actually not so great a guess, and then we look at finer and finer details, and we get more and more information about what this shape really is, and we truncate it then usually at some order, right? And people devote years to doing these calculations at high orders in perturbation theory, and I'm also involved in doing research to try and make these calculations accessible to real-world applications. Of course, this is not quantum field theory. This is a Koch snowflake, but it's illustrating that there are repetitive patterns that you can apply over and over again that also appear in quantum field theory, where it would be sort of a quantum fractal structure, so a stochastic one, not a deterministic one like this, but the underlying principle is there. It's actually very deep. In any gauge theory with massless quanta, so massless photons, QED is one of them, QCD is another one that I study a lot, chromodynamics, where gluons are massless. Any gauge theory with massless quanta, you have at the Lagrangian density level a scale invariance. So the thing is dimensionless. That scale invariance means that you have something else that was really cool in the 80s, not just a chaos. I remember that reading books about chaos and being excited about it. Fractals were also really popular in the 80s, and you had the Mandelbrot set and posters of it and stuff like that. So I really love fractals. And that's part of the connection to infinity. So one of the infinities I wanted to make an allusion to is, of course, the celestial sphere, that we're looking at this two-dimensional thing that is sort of at infinity, where we don't have the radial coordinate or have to do tricks to get it at least. Another sort of infinity is encoded in fractals, where you never get to the end, right? It just keeps on going and going and going, and it's this infinite progression. The rules of it itself is what you study. And that is something that I devote a lot of time to, and I think is really pretty about these patterns in quantum field theory. They correspond to universal structures, universal propagator structures that essentially encode the uncertainty principle in a relativistically covariant way. So you have these structures that are universal in quantum field theory amplitudes, and you can build cascades, Bremsstrahlung cascades, where you emit more and more radiation at ever longer wavelengths, and you keep on going to infinite order. So these are actually calculations that we can do infinite order quantum field theory. In some sort of semi-classical, or classical limits are the easiest. Semi-classical, we can do a few sort of convolutions of these orders. And we formulate these evolution equations as differential evolution equations, where we start basically with this kind of, whatever the leading order calculation is. Again, it would be the triangle in the Koch snowflake case, but whatever the leading order amplitude is as a mathematical structure. And then we start putting crinkles on it. And these crinkles are Bremsstrahlung radiations at longer and longer wavelengths, but because gluons are color charged, you emit a gluon at some wavelength, then that gluon will emit further gluons, and those gluons will emit further gluons, and you've got a whole cascade of Bremsstrahlung, which we call jets of radiation. And stochastic solutions to these evolution equations we do by Monte Carlo. So that's what I do, Monte Carlo event generators. We call them parton showers. Partons are a common name for quarks and gluons. So these generate radiation. When you kick them, an accelerated charge will radiate, but that is an acceleration of a charge, and so that will generate more radiation. It's just radiation of accelerated charges, but in a quantum field theory context. And then we can build in scaling violations. It's not an exact fractal, it's only approximately. We have running couplings, we have masses in the game that break the scaling invariance. We can build in those effects as well. And I find those patterns quite pretty. And that's something that I wanted to share with you and show you. Now, of course, this is again just the Koch snowflake. It's not the actual quantum fractal that I have in my mind, which I would love to communicate better than this. But so this desire to communicate this in a way that's at least inspired by the beautiful pictures that we have in astronomy made me think about, well, this fractal substructure that we have in particle radiation patterns, that generates these beautiful, very complicated events that we see when we look at event displays. And what we do with them is we cluster all this structure back to find the hard substructure, the jet-like structures or whatever we have at the beginning of the day to see what actually went on. And we use something called jet clustering algorithms for that. It's the main tool that we use to analyze and simplify these very complicated reactions that we see. So one way of doing it is called sequential recombination. You look at all these particles, you have a resolution measure, can be their opening angle, can be the invariant mass between them, some resolution measure, and you find the two that have the smallest resolution measure, you combine those two, you keep on going, and you construct a tree out of your whole event that clusters it back to a starting point. And if you sort of invert the quantum structures, the propagator structures in the right way, you get a good picture of what a classical approximation to the event would be. So you iterate that until only everything is a single blob, and then you kind of have an evolution of the event. So the idea that I had was to capture this way of looking at events and to look at not single events, but statistical samples of events. So instead of an event display with a single event, have an event display that integrates sort of a long time exposure notion that you have from astronomy, and to look at events in momentum space, which is more like what we look at them as scientists rather than in configuration space. So I played with some graphics libraries, and I've never shown this in public before. So I designed for this symposium Astro-inspired long-time exposures of particle physics reactions. So it's the first try, and they're not as pretty as astronomical images. But what I've done is, on the radial coordinate, so it's sort of a polar plot, is this resolution measure. And I use a familiar one that to particle physicists this will be familiar. It's analogous to where you are in the fractal. So the fractal sort of scale, how deep you are in the fractal, that goes out. And that means that things that happen early on are near the center, and things that happen late are further out. The angular coordinate is just the polar angle with respect to when you've clustered everything back to two jets. So that would be the original QQ bar pair that seeds the radiation. So they will be on the horizontal axis. And then for color scale, I simply used the energy of these quanta, the frequency. So I just simply colored them the way that, so color scale is sort of normal, except of course these things are all particle physics energies, so they have nothing to do with human wavelengths, but you know, astronomers do similar things outside the visual spectrum, right? So this is the first thing that I did, which is a picture of a lot of E plus E minus to 2 jet event or to QQ bar events, which then generate radiation. And you can see the 2 jet structure very clearly. So close to the center, you have the blue structure. So high energy jets, a lot of these, the high energy bremsstrahlung radiation will be at large angle. So there's blue stuff going up at large angles. The closer it gets to the vertex, the harder this substructure is, the earlier it's generated. And so the blue stuff will be generated quite early. But you can also, if you're doing collinear bremsstrahlung, then at later times you can split collinearly into 2 quite hard pairs. So there's also blue structure here. You can also see that there's an asymmetry in this plot between this hemisphere and that hemisphere. That's because a lot of these events, about a third or a fourth of them, this is just all events, are 3 jet events. So they will have a 3 jet structure. And this is overlaid on the 2 jet structure that you have, which is the dominant structure. But this is all sort of just the long time exposure of all events. You can also see that the red spectrum is much more uniformly distributed. And that is an artifact of confinement. So the red color is for energies that are sort of order the confinement scale in QCD, where we get confinement and quarks and gluons bind into hadrons. Everything else, the blue and the green, they are perturbative bremsstrahlung of gluon and quark radiation The red is where we start to see pions and kaons, hadrons come out. And because of the confinement field stretched between the two quarks, that will be rupturing into particles along the axis. So even if I have most of the bremsstrahlung going in the forward direction, there will still be a confinement field between them, which will give soft particle production over the full solid angle. So one can see lots of stuff in this picture already, but just like, you know, when we look at the sun or we look at stars and whatever, astronomers immediately start putting filters because they want to isolate certain things. And I thought, well, you can also put filters in this representation. So for instance, you can put a two-jet filter. Now I've filtered out the three-jet events. And so now you don't see this stuff going off at high angles anymore. You just see that there's a red structure here. These hadrons are coming off at all angles still, because there's still the confinement field between them. But there is no extra resolvable jets. This is really just two jets going off to the sides. You can also then say, well, what about the other ones? We can put a three-jet filter. And they look beautiful too. So here you really see a three-jet event with blue structure coming off the two-jet event. And there's lots of other games one could play, I think, with this way of visualizing particle collisions, but the main point is that here I'm really taking exposure of the interaction point. And this is actually physics too, that blue dot. It's not just visual candy. It's one-jet events. So there's an explanation for why that looks the way it does. But yeah, I find these
Isn't it magic?
pretty, aren't they pretty?
Yeah. Just before you press, return, the moment before you see it for the first time, it's like,
Yeah,
wow, and then boom.
yeah. I didn't know it was going to look like this.
Isn't that great?
Yeah. These are TT bar events, so a completely different type of events, E plus E minus to top quarks. They have very much sort of ultraviolet structure in them, and then multiple jets. So also quite pretty. Okay, thank you, Rosemary, for being such an inspiration. And here's a little quote from Marie Curie.